Then after we've talked about the Sn2 reaction, we can of course talk about the Sn1 reaction. And in that case, the reaction mechanism is a little bit different. Here we also start with our halogene alkane as we've just seen before. But in this case, we are not having this linear transition state where our nucleophile attacks while our leaving group leaves the molecule. But we have a different reaction mechanism, and that is where the leaving group X leaves here now together with this lone pair, and an intermediate carbo-cation is formed that is planar in geometry. It's again sp2 hybridized as we've seen also initially, and now only in the second step our nucleophile attacks this intermediate carbo-cation from either side, so from the left or from the right in this case. And we are now not having this Walden inversion effect, so we are not keeping our stereo information that we have on our carbon atom, but 50% of our nucleophiles will attack from the one side, so we are just doing the inversion, and the other 50% will attack from the other side, and there we retain the same configuration at our molecule or at our carbon atom. And so we are getting again from a single enantiomer that we maybe started with, we get a racemic mixture of products. And in the Sn2 reaction we didn't get that. There we exactly kept all the stereo information, so we transformed one enantiomer into another enantiomer pure product component. And this is very different. Why is it called Sn1 reaction again? Sn1 because it only depends on the concentration of the starting organic molecule here in this case, because the rate determining step is actually the first one where our leaving groups leaves our molecule. The other step here, the second step, the attack of the nucleophile, is fast. So the concentration of the nucleophile is not important, because in the end, whenever a carbo-cation is formed, then there's always be a nucleophile that attacks it, and then the reaction proceeds. So this is not important, but just the concentration of our starting material. Also, our energy diagram changes here again. We are now having an intermediate. Again, a brief reminder, be aware of the difference between intermediate and a transition state. A transition state is just something that is like, that's not actually isolatable, so it's not like a sink, not a thermodynamic sink. You have seen that before. That's always on top of this energy hill, basically. And the intermediate is in between two hills. We get like a species that is somewhat stable, of course still very reactive in nature, but we can, under certain conditions, we can isolate that. And that's an intermediate compared to the transition state here.